Okay, let's do our last application of the envelope theorem to a problem in microeconomics. And in fact, we're actually going to apply it to two analytically identical problems in microeconomics, one theory of the firm and one in consumer theory or demand theory. We'll start with the theory of the firm application. And what we're going to do is look at Shephard's lemma. And we're going to use these axes over here to draw a diagram of what's going on. Now, Shephard's lemma, that was advanced by Ronald Shephard, who was actually an engineering professor at Berkeley back in the 40s, maybe 50s and 60s. And he did this in a famous book back in the early 50s on production and cost functions. And so what's Shephard's lemma about? Well, let's suppose we have a firm that's maximizing profit. And of course, profit is by definition revenue minus cost. So whatever output the firm is going to produce to maximize profit is going to minimize, if it maximizes profit, then since cost is subtracted to get profit, it's going to minimize the cost of producing whatever that output is. So the firm's objective isn't to minimize cost, but it is to minimize the cost of producing whatever it does produce to meet the objective of maximizing profit. And in fact, Shephard's lemma gives us results that apply even to firms that are not maximizing profit. We could have a firm that is maximizing market share, maximizing sales, or we could even have a firm that is maximizing profit, but it's not a price taker on the revenue side, not a price taker in the market for its output, but we are going to be assuming that it's a price taker in the markets for the inputs it uses to produce the output. So how are we going to model this? Well, let's start by saying that the firm has a target, let's say a target level of output that it's going to produce. And so that, let's say, we'll just use Q for that. And in order to produce that level of output, it's going to have to use inputs in its production process or production function, and we're going to just use two inputs. But of course, everything we do, we could do just as well for any number of inputs. It's just a little clearer and more transparent if we do it with two. And so the firm is going to choose the levels or the quantities of these two inputs that it is going to use, it's going to purchase in the marketplace for the inputs in order to produce the output level Q. And what it wants to do is it wants to choose those inputs, the input combination, to minimize the expense of producing the output. So we'll use capital E, and I'll call it the expense function. Actually, when you're looking at any microeconomics book that does this, almost none of them give a name to this function or even a notation for it. They just write out the linear function. But we'll actually write it as a formal objective function. And so here's the amounts of the inputs that it's going to use. And here are the prices of the inputs. And we said we're going to assume that this firm is a price taker in the market for its inputs. So that means that the price that it pays for an input isn't going to be affected by how much it purchases. So that means that the expense that it will have to lay out to obtain the input combination of X1 and X2 will be this, where the W's are the prices of the inputs. And I'm just using W's as a notation here because that's completely the standard notation that people use in this context. And so the firm wants to minimize the expense of the input combination that it is going to choose, but it's got to choose an input combination that will actually achieve the output level Q. So let's go over here and draw a little picture of this. And I believe this is probably something that most of you will have already seen in your undergraduate program, perhaps in intermediate microeconomics course. And the diagram, I presume, will be familiar for that reason. But I'm sure that you haven't seen it as an application of Shephard's lemma. The results that we'll get are not the kind of results you typically get in an undergraduate program, and we're then going to turn around and apply everything we do to demand theory, which I'm pretty sure you wouldn't probably not have done as well. So let's draw first a level curve of the objective function. It's a linear function, so the level curves are straight lines. And of course, these are the things you may have called isocost lines or isocost contours. You did this before. So here's a couple of the isocost or level curves of the expense function. And then we have the constraint here. And so that constraint is that we have a particular level curve of the production function, in particular, the level curve for output level Q, and this you've probably called an isoquant. And let's put in maybe another isoquant, let's say maybe about here. And of course, they're all the way through the space here. And so now let's put in here the gradient. Well, it's the gradient of the production function. And let's put in here the gradient of the E function, the objective function. And let's note too, by the way, that this is a contour of the objective function. So this is, let's say, just W1x1 plus W2x2 for particular x1 and x2. And so, of course, what the firm wants to do is not go in this direction like in the consumer theory problem, but the firm wants to go in this direction to minimize the expense, but it can't go below the isoquant or level curve for Q. So this would be perhaps an isoquant for maybe a Q tilde bigger than Q. So that's our optimization problem, in this case a minimization problem. And the parameters of the problem, so we've been using theta for the vector of parameters, and in this case those parameters are the target output level and the input prices. So these are the elements of the problem that the firm is taking as exogenous or treating as parametric, as parameters. Now you might say, but hey, wait a minute. The firm doesn't really take the level of its output to be exogenous. It's not imposed on it typically. It chooses the level of output. But of course, what we're doing here is we're saying it is going to choose the level of output, but for any hypothetical particular or target level of output, then we can take that as given in our problem to minimize expense, to minimize the cost of producing that output, and that will be a parameter in that problem, but then we can see what happens as that parameter varies, and that, of course, is very much a kind of envelope theorem sort of problem. Okay, so what I want to do first is I want to get all the variables and parameters in one function on one side of my constraint equation. So I think we've done that once or twice before already. I'm going to define a new function. I'll call it g of x1, x2, and q, let's say, and that's going to be just f of x1, x2 minus q. So notice a couple of three things there. One is that I wrote this without all three of the parameters in the function. Now I could have stuck those parameters in there. That wouldn't make it wrong, and this isn't wrong. But the point is that the function doesn't actually depend on the two input prices. It just depends on the x1, x2, and the parameter q. So let me just point out here that I didn't write in a W1 or a W2. We could put them in or not. It doesn't really make any difference here. And the same thing is really true up here. Here, I've got the decision variables and two of the parameters, but here, there's no q. Again, I could put the q in here, but the function actually doesn't, in the end, depend on q, independent of q. Second thing to notice is that I wrote this as f of x1, x2 minus q, but I could just as well have written q minus f of x1, x2, and I'd have the same thing because, of course, the constraint is going to be that this is 0. And if I wrote q minus f of x1, x2, then that would have to be 0. So I could have written it either way, but I actually couldn't have written it either way. And the reason is that I want my g function to be quasi-concave. And you can see that the isoquants here, the production function is in fact, strictly quasi-concave, the way I drew it. And so we're assuming here, I haven't written it down, but we're assuming that the production function is indeed at least quasi-concave, if not strictly quasi-concave. We're not assuming that it's concave. So again, this could be a firm that has, for example, increasing returns to scale, which would affect the analysis of profit, affect the analysis of the cost function. So it could have increasing returns to scale, but we're assuming that it is concave so that the marginal rates of substitution between the inputs, the marginal rate of technical substitution, I guess it's often called, that these marginal rates of substitution behave in the usual kind of way. And so we have a concave function concave function g for our constraint, and we're minimizing our linear expense function subject to that constraint. And so now let's actually apply the envelope theorem. So let's start with partial of the value function with respect to either one of the input prices. That's going to be whichever input we're talking about. Let's suppose it's x1. Let me actually take this off, and let's write here that this is we'll be using the envelope theorem. This is the partial of the objective function with respect to wi minus lambda times the partial of g with respect to wi. And so now I jumped ahead a little of where I wanted to be. The derivative of the e function with respect to wi is indeed xi. And I have minus lambda. And I have the partial of the g function with respect to wi, but the w's aren't in here. So that is 0. So this is just xi. This is just the derivative of the value function with respect to this parameter, input price, is just xi. And of course, that's going to be the x, the input purchase or usage, that is the solution, or the xi part of the solution of our minimization problem. And so let's put the parameters in here. So this is just as the parameters vary, this is just the demand function that the firm has for input I. And if I do this for each I get each of the input demand functions. But notice that this input demand function depends not just on prices of inputs, but it depends on the target output level. And for that reason, we refer to this as the conditional input demand function. And it's called the conditional input demand function because it gives us the demand for the input conditional on the particular target Q that we've chosen to put into the problem as a parameter. And then, as I said, we can let that Q vary and see how the input demand varies with output level as well as with the input prices. Let's look at the derivative of the value function with respect to the other parameter, the Q, the output level, the target output level. That's going to be partial of E with respect to Q minus lambda partial of G with respect to Q. That's going to be, well, the expense function doesn't have any Q in it, so this is going to be 0 minus lambda, and the partial of G with respect to Q is just minus 1. So we have here just lambda, the value of the Lagrange multiplier at the solution. And of course, that's not a surprise because we have already seen that the Lagrange multiplier is a shadow value, the marginal value of the right-hand side of a constraint. And so this is the marginal value, the marginal expense that we will have to incur if we want to have one more unit of output. So it's really the marginal cost for the firm. So this is the firm's marginal cost is the value of the Lagrange multiplier in the minimization problem. And in fact, let's go just a little further. Let's note that the value function, of which these are the derivatives, the value function is, of course, just the objective function evaluated at x1 hat, x2 hat, and then we'll put the parameters in here, W1, W2, and I'll even put in Q here. That is, it is W1 x1 hat of the parameters plus W2 x2 hat of the parameters. So that's the value function. And that is telling us what the expense will be to produce Q units of output. In other words, this is actually the cost function. So we don't actually write the value function in this problem typically as V, we write it as capital C because it is the cost function. So this is the firm's cost function. And again, the derivative of that cost function with respect to the output level is marginal cost. It's the derivative of the cost function with respect to output. So that is Shephard's lemma applied to the problem that we have laid out here. And again, let me emphasize two things that I already have emphasized, but I want to mention them again. One is that the Q in the problem is simply a target or hypothetical output level that the firm can then say, okay, as we vary that parameter, as we vary that output level, what happens to cost? That will be the cost function. What happens to marginal cost? This, of course, is going to depend on the parameters. We don't usually write it this way, but this, of course, does depend on the parameters. And we get the conditional input demand function. So the functions for the different inputs. So this is Shephard's lemma. And now this is Shephard's lemma applied to the theory of the firm production and cost. Oh, and the second thing that I want to emphasize here is that, again, is that this is extremely useful, broad class of cases in which this is useful because the firm, if it's maximizing profit, it could be a price taker, in which case we could use Hotelling's lemma and the similar analysis, but it may not be a price taker in the market for its output. This would still be appropriate because the firm would still want to minimize the expense or cost of producing whatever output it produces, and it doesn't even have to be a profit maximizing firm. It could be maximizing, as we said, any one of a number of other possible objectives, but if it wants to do that in a cost-effective, cost-efficient way, it's this problem that reflects what the firm is doing. Okay, now let's close this out by reinterpreting everything we've done here on the theory of the firm in terms of consumer theory or demand theory. So there, every one of the elements of the problem here will correspond to an element in consumer theory. And so let me start, I guess, by just drawing some of those things over here on our diagram. So in consumer theory, we really are, well, if we're maximizing utility, we're trying to go this way to get on the highest indifference curve, geometrically speaking, subject to budget constraint. But what we're going to be doing here is minimizing an expense function. So let me write that over here. Actually, let me take off this because when we are talking about consumer theory, demand theory, we aren't talking about profit and cost. So here, let's write that we're modeling the consumer in a, possibly you could think of it as a kind of an artificial way of modeling it for the purpose of analysis. And that is minimizing an expense function, where the expense for the consumer is how much it's going to cost the consumer to purchase and consume these amounts of the now consumption goods. And so the parameters here are going to be the prices of the consumption goods, just as the parameters here were the prices of the inputs. And of course, this is going to be P1 X1 plus P2 X2. So clearly here, just as we assumed that the firm was a price taker in the input markets, here we're assuming that the consumer is a price taker in choosing its purchases. So we have a consumer that's now minimizing the expense that it has to lay out to get a particular consumption bundle, but subject to what kind of constraint? So what that's telling us, in fact here, let's replace this with P1 X1 plus P2 X2. So now these ISO cost contours are ISO expense contours for the consumer, telling us how much he'll have to spend to get various consumption bundles. And we're going to say that the consumer is doing that so as to achieve some target utility level in parallel with what we did for the firm with a target level of output. So here, I want to replace this with U of X1, X2 equals some target level of utility, for which I'll use a U bar. So this is subject to U of X1, X2 equals U bar. And I could again write this function g. Let's just do that. We have g of X1, X2, and U bar. That's not F. That's going to be U of X1, X2 minus U bar in parallel with what we did over here. And so now, of course, this constraint says that's going to be 0. So that puts us on a target, if you like, indifference curve. And so the parallel with the results that we get from Shephard's lemma, the parallel to Shephard, the application of Shephard's lemma to demand theory then, is that the derivative of the value function for the consumer with respect to one of the prices, that's going to be, of course, using the envelope theorem, that's going to be the partial of E with respect to Pi minus lambda partial of G with respect to Pi. And just like over here, that's going to be Xi hat as a function of P1, P2, and the target utility level. Let's do one thing I did over here that I didn't do down here. Let's put in the parameter vector. That's going to be, well, the parallel here would be that I would have x1, x2, and u bar, but, well, no, over here I wrote q, w1, w2, so the parallel would be u bar, p1, p2, but in fact, the way that the parameters are typically written in the consumer theory application of the of Shephard's lemma is to put the price parameters first, followed by the utility target level. So it's as if I took the Q and I moved it to the right here. So I've just written it this way because that's the way you're going to see it when you see Shephard's lemma applied to consumer theory. And so the parameters show up in here, and this is the consumer's demand function, but not the usual demand function. It's not the demand function where we determine the consumption or purchases as function of the prices and the budget or income. It's as a function of the prices and the target utility level, with the consumer minimizing his expense. So this is actually referred to as the consumer's Hicksian or compensated demand function. By the way, the notation used here in the theory of the firm application of Shephard's lemma, I think just about everybody uses the same notation, and the notation I've got over here is quite standard. Over here, the notation varies a lot. People, of course, use P's for the prices, and they use X's for the decision variables, but they use different notation for the utility target, and they use different notation for sure for this function here. They'll use H for Hicksian demand function. They'll use X super H for Hicksian demand function. So here you're going to see that just about every graduate micro textbook uses a different notation over here for some of the items over here. But they all use the same terminology. It's the Hicksian or compensated demand function, which plays an absolutely central role in demand theory. And then we have the partial of V with respect to Q over here, so that would be with respect to the remaining parameter over here, which is U bar, and of course that's going to be just the value of the Lagrange multiplier, just like over here, at the optimal solution. And you'll notice this is actually the reciprocal of the lambda in the direct utility maximization problem that we usually ascribe to the consumer. So there we found, I believe, in the previous example that we just did, that the Lagrange multiplier was the marginal utility of an additional dollar in the direct problem. Here, it's the marginal dollar that you have to spend to get an extra utility unit, if you like. And so that lambda is going to be the reciprocal of the lambda over here. That is, I suppose, a potential source of confusion, but we actually don't use this very much. This, on the other hand, is quite central. And so here, let me just finish this off by identifying, there's one more thing, one more important thing here, and that is, as here, I wrote the value function, and so here, let me get down here where I can write this a little better. The value function for P1, P2, and the target utility, that's of course just P1, X1 hat, the parameter values in here, P2, X2 hat, parameter values in here, and that is actually written typically not as V, just like over here, we actually write this as capital C for the cost function. Here, this is typically written as E of P1, P2, and U bar. E because this is called the expenditure function, and I've been a little careful to refer to this as the expense function. It would be natural to refer to it as the expenditure function, but the problem is when we get down here, this is called the expenditure function, and that's standard terminology, and so I wanted to avoid that confusion. So I'm referring to the E here and here as an expense function. Actually, other people don't really give it a notation or a name, but I think that's useful here. So this is the consumer's expenditure function. And so that pretty much covers everything we need to do here for the applying Shephard's lemma to the theory of the firm, applying Shephard's lemma to consumer theory. And let me just do one last thing here, and that is let me summarize here the translation between the two. So let me first write here the elements of this problem. So we have the expense function, we have the production function, we have the target output level, we have the input prices, and we have the input quantities purchased and used in production. And so the corresponding items over here that are playing the role of these items over here would be, again, I've used E, but of course the prices in this E are the consumer goods prices that we use P for over here. The corresponding to the production function over here is the utility function over here. Corresponding to the target output level over here is the target utility level over here. And of course, corresponding to the input usages, the choices, the decision variables of choosing input levels over here is X's same notation, the consumer's choices of amounts of the consumer goods to purchase. So this would also be Xi over here. And again, just to recap here, the conditional input demand functions here correspond to the Hicksian or compensated demand functions over here. And the cost function here corresponds to the consumer's expenditure function over here. So that's it for Shephard's lemma. That's it for our applications of the envelope theorem to problems in microeconomics. So see you all next time.